All right, welcome everyone to the sixth session for beginner track. Today we're going to be learning about BFS and DFS. On the screen, you can see the link to the slides and also the portal code. Yeah, give you guys a few seconds to grab that. Okay, all right. So on the agenda for today, we're going to go through an example problem to help introduce us to the idea of graphs, because I'm sure not all of you guys are familiar with what a graph is. So we're going to introduce that first. Then we're going to go through traversals of graphs, BFS and DFS, which is the main topic of today. And then we're going to talk about applications of BFS and DFS. And yeah, and then we'll go through two more example problems, and we'll have the contest at the end. All right. So our first problem is called Spy-cpc. So we have been recruited to a very prestigious secret branch of ICPC known as Spy-cpc. And for our first mission as a part of this group, we're going to try and determine the location of a gang leader called Wilson Whisk. So Wilson Whisk has one weakness. He is devoutly loyal to his friends. So he'll always pick up the phone for them. So our goal is to use our mutual contacts to reach him, because once we reach him, other people at Spy-cpc can triangulate his location and we can track him down. So we need to call him, but obviously we don't have Wilson's phone number, but we can get a phone number by calling the people that we do know and asking for the contacts that they have. So for example, I can call Raya and ask for Tony's number, and Raya, because she's a good friend, will oblige and give me Tony's number, and I can call Tony. And I can continue that chain by asking Tony for his contacts and so on. However, we have one last constraint. So we need to find Wilson, and also want to do it in as few calls as possible, so we don't raise suspicions. So this is just a recap of what our objective is. And for our input, we'll be given a list of all known contacts of Wilson and all known contacts of those contacts, and so on. So for example, we're going to be given a list of connections. So we know Wilson's friends with Alvin, Bill, and Lenny. Alvin is friends with Bill, Emma, Farah, and so on, and etc. And it's going to go all the way, trace back all the way to us. So we can see all the people here, and we can connect people together by whether or not if they're contacts. So Wilson is contacts with Alvin, Bill, and Lenny. Alvin is contacts with Bill, Emma, Giovanni, and Farah, and so on. So we can kind of draw this kind of picture relating all the people together. So our question is, how can we find the shortest path between any two people? We want to cross the least number of these lines. So if we are Alvin, Bill, or Lenny, then we know that we can directly call Wilson because we have their number. They have Wilson's number. If we're Giovanni, Emma, Farah, it only takes 2 calls. They have to go through Alvin, and we can kind of keep branching out like this. So the people who haven't been assigned a path length will be assigned 1 plus that path length. So these 2 people here have a path length of 3, and so on. So we can keep expanding outwards. So you can kind of see a kind of pattern showing up where we're expanding outwards for increasing paths. So from this, you can see Rohit is the furthest away from Wilson. So this brings us to our topic of today, is what is a graph? So a graph is a set of vertices and edges. We also call them nodes. We also call vertices nodes. And this represents relationships between objects. So in this example, in this picture here, there's 2 vertices that are connected by an edge. So formally, we define G as a graph, and G has two sets. There's the set of vertices, which is a bunch of numbers, and E is a set of edges, which connects these vertices together. So for example, on the right, you can see that there's a graph with 4 nodes and 4 vertices, 1, 2, 3, and 4, which we can see here. And there are 4 edges from 1 to 2, 1 to 3, 2 to 3, and 2 to 4. So normally when you're doing graph theory problems, they'll give you the information about the graph in terms of the edges that it has. And normally vertices are numbered from 1 to n, where n is the number of nodes. And yeah, but sometimes they can give it in terms of names because it might be something like a bus stop or a train station. They'll give you names instead. So it can be anything you want. So for example, this is a sample input of a graph. So what this means is that in the first line, right, they would give us how many nodes we have. So it says 10, and it tells us the second one is the number of edges there are, which is also 10. And then the next 10 lines will tell us which nodes are connected together. So there's a path between node 1 and node 4, and so on. And there's a path, finally, there's a path between 1 and 10. This is the most often seen representation of graphs that they'll, the type of input that they'll give you. Sometimes trickier problems you'll have to make some logical assumptions and jump to this graph from the information I give you. But most of the time, I would say like 90 to 95% of the time, they'll give it to you this way. Okay, so examples of a graph. We had that contact graph from before. We can also have something like a friendship graph where a bunch of people and people who are friends with each other are connected. Or we can have like a neighborhood graph where it's like a map where there's certain landmarks and there's paths between them. So to talk about graphs, there's a lot more terminology that we need to kind of go over so that we can explain stuff quickly. So we have adjacent vertices. Vertices are that are connected by an edge. So these two vertices are adjacent. And we have the degree of a vertex is how many edges a vertex has. So you can kind of see these only have 1 edges. These 3 nodes have 1 edge coming out of it. So they have a degree of 1. And the bottom one here is connected to a lot of different nodes. So it has a degree of 3. And what is a path? So a path is going to be a collection of vertices from a vertex A to some vertex B, such that so from A to C1, from C1 to C2, and so on, these are all edges so that you can kind of walk between them. So this is intuitively what you would think what a path is. So you can see here, you go from A to C1 to C2, C3, C4, and then to B. And what is a cycle? So a cycle is a special case of a path where the starting location is the same as the ending location. So you can see here, it starts with the same vertex, starts and ends with the same vertex. Other examples of graphs are also grids. You wouldn't really think of this intuitively, but a grid is basically each cell is a node and is connected to its 4 adjacent nodes for its 4 adjacent cells by edges. So you can kind of think about it this way. This is useful for like grid problems where you're working through a grid and maybe it's a game or something. You can think about it as a graph that way. So directed graphs are special types of graphs where the edges have an arrow indicating direction. So you can only go from the left vertex to the right one and not vice versa. So you can see there's an arrow there. So the terminology for these directed graphs are slightly different in terms of the degree. There's in degree and out degree, which intuitively you can think of as the number of edges going out and the number of edges going in. This is a useful characterization for other advanced topics in graphs, such as like Euler paths or Euler tours. So for example, if we have a graph of different locations and we have flights between them, we want to store information about the flights because maybe some flights are more expensive than the other. So we can put the cost of the flight in this graph. So for example, from where you're starting to Milan, it costs $450, but only costs $150 from Shanghai to Mumbai. And we can kind of characterize these graphs as weighted graphs. So these weighted graphs, each edge is assigned a weight, and these weighted graphs can also be directed or undirected. So possibly the flight from Milan to Shanghai is $100, but the flight back is $200. So there's a lot of different ways, a lot of different combinations of graphs properties that we have. So we're talking about all these graphs, and we want to think about how can we convert this kind of pictorial representation of graphs into our code. So the way we can do that, there are two main ways to store a graph in a computer. There is the adjacency list method and the adjacency matrix method. So the adjacency list method is that we have a vector where each index refers to a vertex in the graph. And then for each vertex, we store another vector of all of its vertices that are adjacent to it. So for example, if there's a vertex 1, it has three adjacent nodes. Vertex 2 has one adjacent node, and vertex 3 has two adjacent nodes. So the pros of this method is that it's very space efficient. So it only stores the number of numbers as there are as many edges in a graph. And this is best for graphs with few edges because we don't waste a lot of space keeping track of the edges that aren't there, which will make sense once I bring up adjacency matrices. However, this method doesn't really work too well if we need to check if an edge exists, because we have to go through the entire vector and check if two vertices are adjacent. It's especially inefficient when we want to, if two vertices don't share an edge, because we have to go through the entire vector to check that it's not in there. Any questions so far? All right. So an example of adjacency list. So we have this graph that we saw earlier. So vertex 1 is connected to 2 and 3. Vertex 2 is connected to 1, 3, and 4. Vertex 3 is connected to 1 and 2. And vertex 4 is connected to 2. So you can see that each edge is actually stored twice. So since vertex 1 can go to 2, we store that. But we also store 2 going to 1. So it's both ways. So this is some sample code for how we can implement that. So either we can use like a vector of vectors, or we can use a vector and an array of vectors, which is what we have here. To include an edge, we're going to push back into the specific vertex at the specific node that we want to push back into. We want to push the vertex that it's going to, and so on. So we can add in these 3 edges. So you can go from 1 to 2, 1 to 3, and you can go from 2 to 1. And then to check if an edge exists, we just iterate through this. So we check. So we're going to be checking if node 1, if you can go from node 1 to node 3. So we iterate through the vertex under node 1, and we check if it's equal. So we go through, we have to check 2, and then we check the next one, and we found it. So we know that there's an edge there. So the way that we can implement for a weighted graph is that we just store extra information for each edge. So you can see here from 1 to 2, there's a weight of 5. So we store 5, and we also store 2. This can be in any order you want, just make sure you're consistent. So the way that we can do that easily in C++ is we can use a structure called a pair. So a pair can store 2 of any variable type. So in this case, we store 2 ints. We can access the first element like this and the second element like this, and we can also set them similarly. So we can do myPair.first equals something to set it. And we can initialize it using these 2 methods, either the makePair function or this very compact method with curly braces. I've never really used the makePair because it's just so verbose. So I would recommend also not doing that. But just for the sake of completion, we have that in here. Okay. So this is some sample code for how we can implement, we can create adjacency lists for a weighted graph. So when we push back both the destination node and the weight of the edge. You can see here, if we want to check if 1 is adjacent to 3 with a weight less than 4, we can do it this way. Okay. So this is like a cheat sheet for how we can implement adjacency lists. So for an undirected graph, as I said before, we have to store each edge twice, right? From node A to node B, and also from node B to node A. So we need to push it back twice. For directed graphs, it works basically as like half of an undirected graph, where we only store if an edge exists from A to B. And for a weighted graph, right, we store vectors of pairs instead of ints. So moving on, we have adjacency matrices. And the idea here is that we create a matrix, a 2x2 or 2D array or a vector of vectors, where an entry is going to be 1 if there's an edge between the two vertices and a 0 otherwise. So the pros of this is that it's very easy to check if two vertices are adjacent. We just need to index into the array or vector of vectors and just check if it's true. However, the cons are if there's a lot of unnecessary space in graphs without a lot of edges, right? We're going to store all the non-edges as well. So this is generally good for graphs with a lot of edges, also known as dense graphs, where everything is almost fully connected. So you can see here, so an example of this. So we have that graph from before. You can see that there is a path from 1 to 2 because this is a 1 here. Oftentimes we set the main diagonal to 0 because most of the time when we talk about graphs, we don't talk about paths from the node to the node itself. Some problems might have that, but generally problems specify, oh, there are no self edges. You can see here, and one thing you can probably notice is that this matrix is symmetric in the sense that if you draw a line across the main diagonal and flip it over it, you can see that it's symmetric. It's the same on both sides of the diagonal. And that basically just means that it is a directed graph, right? Because if you can go from one edge or from one node to the other, you can go from the destination node to the original node. So the implementation for this, we're going to create a 4x4 Boolean matrix and we can set them to true. And to check if an edge exists, we can just check that specific index. And one quick note here is that most of the time in problems, they'll give you the nodes one indexed, but generally in problems, it just depends on whether or not you're consistent. So you just pick if you want a 0 index or 1 index nodes. So in this case, there's kind of a waste of space here because there are 7 more like Booleans that we're not even using, right, for the node of 0, since we only have 3 nodes here. That's just a quick remark there. Okay, so yeah, so we just check right here. So the implementation is an implementation cheat sheet. So same as the adjacency list, for undirected graphs, we have to store each edge twice. For directed graphs, we only need to store it once. And then convention is normally you go from the row to the column. So if you want to set an edge from 1 to 3, you access 1 first and you access 3. That's just normally by convention. You could do whatever you want as long as you're consistent. And then for a weighted graph, it's a lot easier. So instead of using a Boolean array, we could just use an int array, and then we could just set the value in there to the weight of the graph. And if there's more information, for example, if you want, I don't know, if there's a road with a certain distance and also maybe a toll fee, then you can just have 2 of these 2D matrices and just store more information that way. So this works well if there are no edges in a weighted graph of weight 0, or else you're going to have to possibly have another like Boolean 2D array if there are many possible values for weights. So now that we're done talking about graphs, we can move on to graph traversals. So how do we go through these graphs and look for paths or cycles or whatever we're looking for? And the 2 main ways of doing that is going to be BFS and DFS. These are acronyms. So the 2 ways do it are breadth first search and depth first search. So for breadth first search, we're going to start at some vertex, explore all the adjacent vertices, then explore all their adjacent vertices, and so on. So it's like working your way outwards. So you can see here, we start at node 1, then we go to all of its neighbors, to 2 and 3. Then we go to 4, 5, and 6, as those are the neighbors of those neighbors. So this is the same way that we traversed the graph earlier in the Spy-cpc problem to find Wilson Whisk. So for depth first search, we're going to do something slightly different, where we start at some vertex, explore as far as possible along that vertex, so along that branch, and then backtrack and go to a vertex that we haven't visited yet, if we run out of vertices. So if I backtrack, we mean return to the earliest vertex, has unexplored neighbors, and explore those neighbors. So in this case, we're going to go down, all the way down. So we go to 2, then to its adjacent vertex 3. Then we backtrack all the way up and go to this one. node 4, which has been unexplored. And finally, we explore this. So our ordering of our exploration is going to be slightly different from BFS. So we're going to run through BFS by hand first and see kind of what sort of process that we have. So we're going to record the unvisited adjacent matrices. We're going to mark them visited and then explore the next vertex. So we're going to kind of keep track of the vertices that we need to visit as well in some data structures that we're going to talk about later. So it's going to be on the right here are going to be the vertices that we want to visit. So we're going to start at this first node. So if there's a gold circle around it, then that's the current vertex that we're working on. And if we have this icon on it, that means we've already visited it. So first things first, we have to set the initial vertex to not visited. So we don't visit it again. Then we check all of its neighbors. So we have 5. That's the only neighbor. Going to mark it as visited and add it into this vertex to visit. Then that's all the neighbors. So we're going to move on and we're going to pick the next vertex that's being pointed to in here in this list of vertices. So we're going to check all of the neighbors of vertex 5, which is these 3, and we're going to add them in to this set of vertices and mark them as visited. Then we're going to remove 5. We're done with it. We've already checked all of its neighbors and put it into the list. And they're going to grab the next vertex, which is 2. So you can see how this arrow is moving down as we keep adding in things into this list that we have here. So we check all the vertices and repeat. So we look at all neighbors, add into the vertex, mark them as visited, and then leave. Go to the next vertex. 9 has no neighbors, so we don't do anything. 10 has 1 neighbor, we add it in, and so on. All right, keep going. There's 2 more for 3. Add those in. Yeah. So I guess you guys can kind of see the point. So we're going to go through them all in order of kind of seeing them, seeing the vertices. So what type of structure do we have for this list of vertices here? So we're going to have to keep track of the first value that we put in. So for example, if we put in vertices 2, 9, and 3, we want to grab the one that we added in the earliest. So in this case, it would be 2. So when we take it out, we want this kind of arrow to the next value that we're going to pull out to shift downwards and look at the second earliest added vertex. And we take it out and so on. So the 2 important things for programming BFS is that we need to keep track of which vertices we already visited. Because if we don't keep track of that, we could go in a loop where we check a vertex, go to all of its adjacent vertices, and then we somehow cycle all the way back, and we'll just be searching forever. And also which vertices we need to keep next. So our list of vertices that we need to visit. So to keep track of which vertices we have visited, we just keep track of a vector of Booleans, which says if we visited it or not. And then what vertices we need to visit is a little bit more tricky. So in BFS, we want the vertices that were added in first to get taken out of the list first. So we want to look for some data structure that has a first in, first out property. And that's going to be a queue. So if you think about a queue as in like a line, right? People that enter the line first are obviously going to be the ones that leave the line first. So a queue is already implemented in C++ nicely in the standard library. We can include it by including queue, or we can just use the bits.std C++ import. So we declare a queue like this, so we can specify what we want to be in the queue. We can also have a queue of doubles, a queue of pairs, a queue of anything. So we can push values into the queue by using the push function. We can grab the value at the front of the queue using the front function. We can pop out the value, so we can delete the first value using pop. Pop doesn't return the value that you removed, so you want to use front first, then pop it out. And then we also want to check when if the queue is empty, because that means that there's no more vertices to visit and we're done. So we want to figure out when we're done visiting all the vertices, we can use this function. There's also like .size to figure out how many values on the vertices, but empty pretty much works for everything that we need to do with it for BFS. The BFS pseudocode is here. So we create a queue. We mark the starting vertex as visited, so we don't visit it again, and put it into queue. And then while the queue is non-empty, so while there are still vertices to visit, we're going to grab the vertex at the front, check all of its neighbors that have been unvisited, put them into the queue, and mark them as visited. And then we pop out the vertex that we're currently working on. So some example code for this is as follows. So you can see we use the queue. We check while it's not empty, we're going to keep popping things out. And we're going to, so in this case, we're using an adjacency list. So we can iterate through the adjacency list to look for edges. We can also do this using adjacency matrix. So we just iterate across the entire length of the matrix. Okay. Any questions about BFS? So for DFS, we're going to do something very similar. And we're going to go to unvisited adjacent vertices, mark them as visited, and explore the next vertex. And the big difference between DFS and BFS is how this list of vertices that we need to visit operates, where the next arrow actually goes to the last added value instead of the earliest added value. So first, we mark the starting node as visited. Then we look at all the neighbors, we add them in. There are no more vertices to visit, so, or no more adjacent vertices. So we grab the next vertex in this list, which is 5. Look at all those neighbors, add them in. Notably, this next goes all the way down to the last added vertex, or the latest added vertex, which is 10. There are no more adjacent vertices, and we grab the next vertex, which is 10. And then this arrow moves up to the second latest vertex that was added to the list. Look at all the neighbors of 10, this is 4, 14, mark as visited, and we continue like this. Does this make sense? Process? Okay. So what type of structure do we have here for our list? So for example, we put in 2 and 9. That means the next item that we grab from this list is going to be 9. When we grab it, we're going to shift our next value that we need to grab up by 1, which is going to be pointing to 2. However, if we add in another vertex, let's say vertex 3, this arrow is going to shift all the way down to the value of 3 because that was the one that was last added. When we pop it out, it goes back to 2, and then we can pop that one out. So once more, when we want to implement DFS, there are 2 things we need to keep track of. So we need to keep track of which vertices we visited. So we've already done that. It's the exact same as BFS, where we keep track of a Boolean array. And we also want to keep track of which vertices we're going to check next. So in this case, we don't want a first in, first out. We want first in, last out, or last in, first out, which is the same thing. And this state data structure exists. It's called a stack. So you can think of it as like a stack of books, where we put books on top of the stack. We have to take those ones off first to reach the ones further down. That's why it's called a stack. So a stack is another standard library implementation, and we can create a stack like this, and we can store anything in the stack, doubles, floats, whatever we want. And oops. And we can push values onto the stack with push. We're not going to use front to grab the element that next is pointing to. We're going to use top because we want the top of the stack. And we're going to pop values off with the same pop function and the empty function to check if there are values in the stack. So we can implement it very, yeah. Top is going to be the last element added, yeah. So in this, it'll be whatever next is pointing to. It'll be grabbing. Yeah, push adds it on to the top of the stack. So you want to think about it like kind of vertically, where when you push something on, it goes to the top of the stack, and then top grabs the thing on the top of the stack. Yeah. Okay, and we can implement this similarly to BFS in a very similar manner, where we just grab top and we use, instead of using front. However, we can also implement it recursively. So this is kind of the main allure of DFS, is that we can implement it really quickly, because in BFS, we have to create a queue object, which is really, really annoying. Well, it's a little annoying. But DFS is so much simpler. Like this is only 4 lines, and this allows us to do effectively the same thing as BFS. So if you guys are familiar with recursive functions are functions that call themselves. So each time this function is called, it basically means that we're going to look at this vertex that we're calling. We're going to set it equal to true, and then we're going to check all of its neighbors. And then if any of its neighbors have not been visited, we're going to go down and visit that vertex first. And then this is going to go all the way down and visit all of the vertices that are neighbors of that vertex. And then we're going to backtrack all the way up and then go to the next vertex. So doing DFS this way might seem a little unintuitive, but once you get the hang of it, it's a lot easier to implement. And it allows us to do some nice things on the graph, which we won't talk about this time, but it's definitely useful. So this is kind of the cheat sheet for that. So depth first search, we kind of go down the graph. Breadth first search, we kind of go across. So you can kind of see if we start at the very top node, kind of goes horizontally across. And yeah. Okay. So why are we learning about BFS and DFS? It just seems like some way to go through a graph, but what can we actually use it for? Because there are certain properties of graphs that are pretty useful. We talked about cycles in the beginning. In our Spy-cpc problem, we talked about like distance, this kind of sense of distance. So what can we do with this? So the first application of BFS and DFS is shortest path. The only way to do this, we can't really do this with BFS, with DFS, but we can do this with BFS. And we want to recall how we found the shortest paths to Wilson Wisp. So we went through all the adjacent vertices of Wilson Wisp, and we gave every adjacent vertex an increased path length of 1. So the distance from Wilson Wisp to himself is obviously 0. And when we go outwards, we're going to increment by 1. So the reason why this works is because every time by the time we reach a vertex in DFS, it must be the shortest way to reach that vertex. If there was a shorter way to reach it, then it would have already been reached. The implementation of this algorithm requires only a slight augmentation of the BFS algorithm. So we need to keep track of how far we've gone from the original starting location. So instead of, we can create a new dist function or a dist array. And this is going to be an array of integers to keep track of the distance. And so if we are currently at a vertex V and we're visiting an adjacent vertex U, we would update the distance to be 1 plus the distance to B. And that's about it. However, sometimes we might want to know what the shortest path is. We don't want to just know the distance, right? It would kind of suck if Google Maps just gave you the distance and didn't tell you how to get there. So what we can do here is we can create another array called parent, and it tells us the vertex from which we came from to create the shortest path. So every time we visit a neighbor of a current vertex, vertex V, and we go to its neighbor U, we set the parent of U to V. And then we can recreate the path by kind of backtracking from our destination. So we start, for example, so if we start at U, we can see that U goes to V, and then V goes to W, and so on. And we can kind of create the path in reverse order. So once our BFS is done, we can use this array to backtrack. So a recap of the shortest path, we're going to be using BFS. This works on both undirected and directed graphs. However, this does not work for weighted graphs because some edges might be longer than other ones, and we don't keep track of that. There's ways of doing it with weighted graphs, notably Dijkstra's algorithm, but we won't be talking about that today. So this only works for non-weighted graphs. And so the augmentations that we create, we can do is we can create a parent vector to recreate the path, and we can also keep track of the distances with the distance array. Any questions? Okay. So the next algorithm I want to talk about is connectedness, which we can use BFS or DFS for. So what does connectedness mean? So if you've been given another villain to locate, Blotto Bloctavius, and you want to draw out a graph the same way, and we have this graph, are we able to reach him by calling our contacts? Obviously not, right? Because there's no contact that Blotto knows that we also can somehow reach. So this kind of means that it's like not connected. You can intuitively kind of see that it's not connected. But what does that mean, like rigorously, right? So we define a connected component as a subset of vertices and edges in a graph, such that there exists a path from each vertex to each other vertex. So if this is true for every vertex in a graph, then the graph is called connected. So for example, this graph on the left has two connected components, because on the right graph, these three nodes can all get to each other, but you can't get from one node on the right component to the left component, and vice versa. And for connected graphs, you can see this graph on the right is all connected. This can be extended to directed graphs, but we won't be talking about that today. We're going to be solely looking at undirected graphs, because it's a little bit more complicated when they're directed graphs. Okay. So connectedness. So how are we going to figure out if our graph is connected or not? And the way that we're going to do that is kind of the way that you would do it intuitively is very similar to how we would do it in algorithm. So we're just going to BFS or DFS, which is also known as traversing the graph, until we can't anymore. Right? So the idea is if your stacker queue is empty, but you still have vertices that are unvisited, that means those vertices are not adjacent to any of the vertices that we have visited. If they were adjacent, then we would have already visited them, because BFS and DFS are exhaustive. It's going to go through every single edge and check it. Therefore, they must be a part of a separate connected component. So the way that we keep track of this is we're going to replace our Boolean visitor vector with a component ID vector, and it's going to tell us which component it is in. And when we do the BFS, we're going to give every vertex the same that we can reach within this in the single BFS or DFS, the same component ID. And when we go to a new component, we're going to increment this. And this value is going to keep track of how many connected components we have. So for example, in this problem, or in this case, we're going to start BFS either from any of these vertices here, and we're going to start at a component ID of 1. It's going to go through all of them, and it's not going to visit any of them in 2 or 3. And then we see, okay, are there any more unvisited vertices? And there are, and we're going to BFS from here, from one of these 3. And then finally, we're going to BFS from this final one. So this is a really easy extension of BFS with DFS. And we're going to use it to explore the graph, and we're going to keep track of which component is it. I think this needs to be flipped. This works on undirected and weighted graphs. Yeah, that's a typo. So Tony can go through so this is an example problem we can work on. So you can try implementing our graph implementation that we talked about. And yeah, so I'll give you a little bit of time to read over this problem. It's like 5 minutes, and we'll go over the solution after that.
I hope you guys have had enough time to look through the problem, at least understand what the problem is asking. I will summarize the problem. Essentially, the problem says that you have all these houses, and then house number 1 is already connected to the internet. You want to make sure, you want to check whether or not other houses are connected to house 1 through other houses, indirectly or directly connected to house 1. So for example, if you look at sample input 1, the first line tells us that there are a total of 6 houses, and there are a total of 4 cables currently, right? I'm not muted. Okay. And then the following 4 lines tell us that house 1 is connected to house 2, house 2 is connected to house 3, house 3 is connected to house 4, and house 5 is connected to house 6. We can construct a graph, an adjacency list, to represent this graph. So for example, if we draw it out on the right, we currently have 6 houses, and the house 1 is connected, right? Now, if we add in an edge between 1 and 2, house 1 and house 2, house 2 would be connected to the internet now. If we add in another edge, house 3 would be connected to house 2, which is already connected to the internet. So house 3 would also be connected to the internet now. Now, if we add in another edge, house 4 would be connected to the internet now. However, now if we add in the last edge, notice that neither house 5 or house 6 is connected to the internet. And that's our solution. House 5 and house 6, we would output house 5 and house 6 as our solution to the simple case. Let's take a look at simple test case 3, right? Notice that the 3 edges form a cycle among the 3 last houses, but none of them are connected to house number 1. So house 2, 3, or 4 are not connected to the internet.
So Tony, I have a question.
Yeah.
You mentioned that we should use an adjacency list. Why can't we use an adjacency matrix for this problem?
Oh, really?
Yeah.
Okay. Yeah. I guess for this problem, we use adjacency list because there are way too many houses. If we use an adjacency matrix, we would have to use up at least order n squared number of arrays, integer cells, right? A 2D array would be too large for this to store this data, and that's why we would use an adjacency list over an adjacency matrix. Okay, so the solution to this problem is to first we construct the graph, and then we DFS at node 1. While we DFS, we keep track of the visited nodes. And in the end, all the visited nodes are connected to the internet, and all the unvisited nodes are not connected to the internet. And finally, we just output the nodes that are not visited. So if we look at the example at the bottom, we first construct the graph like this, and then we do DFS at 1. The algorithm would iterate and visit node 2, and then at node 2, because node 1 is already visited, we would go to node 3, and then at node 3, notice that 2 and 4 are its neighbors, right? But node 2 is already visited, so we would go to node 4. And then now we've done visiting all the houses connected to house 1. And house 5 and house 6 are still not visited, so they are not connected to the internet. So we would output these as our final answer. And here's the solution to the problem written in C++. Do you guys want me to go through it line by line? So first, right, in the left column, I declare 2 things that I'll use later. The first one is the graph, which is an adjacency list. And then the second one is the visited array, tracking whether or not I've visited the houses. Okay, now, and then we declare or we define a DFS function. What the DFS function does is that it takes in one parameter, which is the ID of the house that you want to visit. And then first, it checks whether or not the house is already visited. If it's already visited, we don't do anything. We don't want to do anything. It's already visited. If it's not visited, we visit this house by setting the visited array, the corresponding slot in the visited array to true. And then we visit all the nodes connected to this house by running DFS on each of the adjacent nodes. Right? So notice that this DFS algorithm is very short. It only takes 4 lines, and it's very easy to write. Now on the right, wait, there's a question in the chat. Well, this code gets runtime error. No, I don't think so. I think I try to submit it and it passed all the test cases. Yes, I think this code should work. Wait, did it not work for you? I'm gonna try it later too. Yeah. Okay, so on the right-hand side, we first take the input, right? Basically, the first line tells C++ to take input to like report N and M, and then we assign, we create the two vectors we need, the first visited array and the adjacency list. And then after that, we construct the adjacency list by taking the rest of the input. And then we simply just do DFS1, tell the program to run DFS at node 1. And after that, we should know that like after running DFS, the program would already record all the visited houses in the visited array. So all we need to do is to go through the visited array and check whether or not there are houses that are not visited. So that's what the final for loop does. First, we create a Boolean variable called allGood. We first set it to true, and then we run through the visited array to check whether or not any of the houses are still unvisited. If there exists an unvisited house, we set allGood to false, and then we print out this house's ID, right? If it's like if all the houses are connected, then we would finally output connected in the end. So this is the code, the solution to this problem. And at the moment, I don't see any problem to it. I hope there's no bug in it. Anyway, if you can't, if it doesn't work for you, I'll try it out later. So, Robert.
Yep. Okay, so continuing with our topic of BFS DFS applications. So we've had two algorithms, two of which that work with BFS and one of which that works with DFS. So to give DFS some more love, one application of DFS is also for cycle detection. So we mentioned before what a cycle is. So a cycle is a special type of path that starts and ends at the same vertex. And we want to figure out whether we can detect a cycle. So why do we want to know this? For example, if we're biologists and we're studying food chains, we want to know about cycles. If, for example, mussels all die out, then the predator of mussels, octopuses, I think, will all die out. And the bacteria will also all die out because bacteria will feed off of the octopus and so on. So cycles are kind of important when we want to look at, for example, like this example are like food chains. So if we look at a graph here, our intuitive method of thinking of detecting cycles is that if we try and visit a cycle that we've already visited before, then there must be a cycle there, right? Because if we visited it before, that means we've gotten to it by some other path. And that means that if we somehow reach that node again, then a cycle exists there. However, this doesn't really work for this example, which is a directed graph, because you can see that this is not a cycle. This is, we're coming from this top node here, and we're coming down with two paths, but this path isn't a circular, isn't a cycle. We can't really work through it this way. So recall how DFS works. So we visit the vertex, push in the stack, visit all of its, as we say, ancestors. So all of the vertices that it points to. And once we're done doing all that, then we pop it off of the stack. So how we can use DFS to detect a cycle is not to check if a vertex has already been visited or not when we reach it, is whether or not it's in the stack. So this seems kind of unintuitive, so I'll explain kind of the logic behind it. So if we reach a graph, or if we reach a node that's already in the stack, what does that mean? So that means that we can go from the current node that we're at to a node that's in the stack. So for that to be a cycle, right, that would mean that the node in the stack, we would have to find a different path to the current node that we're looking at. And we can prove that this is true based on the way that DFS works. So if we have a node in the stack, that means that all the nodes that it visits afterwards are its ancestors. So are somehow you can get from that node in the stack to the current node that we're looking at. And since that's the case, we know that we can go from the node that we're looking at to the node in the stack, and we can go from the node in the stack to the current node that we're looking at. And that's going to create a cycle. So the way that we can keep track of this, because we can't search through a stack, Tony mentioned this earlier when someone asked a question, is that a stack, we can only look at the top part of a stack. We can't look at the whole thing in the stack, iterate through the entire stack. So what we do is we create augmented matrix, another Boolean matrix that keeps track of if a vertex is in the stack or if it's not in the stack. So every time we pop out a vertex from the stack, we remove it, we set it to false, we set is in stack to false, and vice versa for when we push something into the stack. It's a little unintuitive, but I hope you can get kind of some sense of why this works. And if we want to determine the actual nodes that make up the cycle, we can do a very similar thing to how we determine the shortest path, is that we create a parent vector that keeps track of the origin of the path from each vertex. So this works on directed graphs, which means it also works on undirected graphs, and also works on weighted graphs. And yeah, any questions? Cool. So in all, we have a BFS versus DFS cheat sheet. So breadth first search, we explore all adjacent vertices first. DFS, we explore as far as possible before backtracking. So those are the two differences. A breadth first search uses queues. Depth first search uses stack. BFS can be used to find shortest path and connected components, and DFS can be used for cycle detection and also for connected components. And the one extra plus that DFS has is that we can do it recursively, which makes it easy to implement. It's just a mean. Okay, and now we're going to get to our final problem, problem C, final example problem. So we'll give you a few minutes to look at that. And we'll go over the solution in like 5 minutes or so.
Okay. All right. So you've read the problem. Do you like understand it? Do you want me to walk through like test case? Okay, I'm gonna walk through a test case. So what's happening basically is we have these letters coming in, and these pairs of letters just say that the first letter can also be interpreted as the second letter. So for example, we could say like C. Like that. If C comes in, you can also read it as T. If I comes in, you could also read it as R. If K comes in, you can also read it as P, and so on and so forth. So we have this coming like this, and we end up with this directed graph of, letters that can be read as all the letters that come after them. And so let's say we had like the test case can and the. Can be the. We could look for C. Can C be read as T? Where C is, of course, the first letter of can, the first letter of the word can, and T is the first letter of the word the. So C can be read as T, so that works. And then can A be read as H? There is no A in here. So A cannot be read as H, and that's that. But it works differently without and the. We see that O can be read as a T, because you go O, T can be read as C, this can be read as T. U can be read as H directly, and T can be read as E directly. And so that's how the problem works. Now that you have that, do you want an extra second to like think about it, or would you like me to delve into the solution? Or raise your hand if you would like a little bit more time to like think about it or try and implement it. Okay, cool. Well, then we will move on. So the solution, ultimately, the thing with graph problems is that a lot of the big part is implementation. So basically, the way that we're going to solve it is by doing what we just did, which is build this graph and then traverse it and see if we can find the ith letter of the second word and if it matches the ith letter of the first word. And that's it. But the part that is going to be difficult-ish, as it often is with graph problems, is the implementation. So here's what the final code is going to look like, just so you can see it. And so when I go through it, you have some context. And now I will go through it. All right, so we just start by taking in the characters that we're given, which I'm building this adjacency list. So this list right down here is the same thing as this graph over here. And so as you can see, you just take in the two characters, and the first part of the graph represents like the letter, and the second part represents everything that it can be read as. So you see, E can be read as H, C can be read as T, just as same thing as in this previous graph right here. All right, so this is the adjacency list code basically that you learned earlier. It's fun. And then we're going to be creating a function. All this page is saying is we're going to create a function called solve, which will take the first word and the second word and see if they can be read as the first one can be read as the second one. All right. And if you're not comfortable using functions, you don't have to do that. I wrote it this way so that it could be easily split onto these slides, but you know, you do what you want to do, of course. All right. So how will we solve this? What we're going to do is if the length of the starting string is not equal to the length of the ending string, of course, they're not going to be the same word. And this is helpful because we don't have to use like min of start length and end length, whatever. We could just include that for ease. And now the meat of the solve function is we're going to have this. This is exactly basically what we said we're going to do. We have this vector of bools, which would be the like visited vector. And then we'll have a DFS function, which we'll define in a second, but this is basically just the DFS function you learned in this workshop. And then we'll run through it starting at the ith letter of the starting string. And if at the end, the ith letter of the ending string, we never visited it, then that means that these two strings cannot be equal. Does that make sense? Okay, cool. Yeah, so and then at the end, if we get to this point, the point where we went through all of them and none of them have failed, then they've all succeeded. So, and we succeeded, so the words can be one another. And so lastly, we just have this DFS function, which is basically exactly what you learned earlier. We just have our visited vector. We say we visited it, so it's now true that we visited it. And then we'll go through all the neighbors. And if we haven't visited them, then we will visit them. And that's it. And if you would like to see a simulation of that with our test case is on the slides right here. We're going through O, C, you know, whatever. And you can run through this. I'm not sure how helpful this would be, but yeah, in case you need a visualization of the DFS, it is here for you. And just C++ syntax, if you're passing it into like a function, don't forget to use to pass it, you know, by reference, if you're going to use this code. All right, and that is the entirety of the code. So all we did was we went through, we filled in the graph, and we traversed the graph for each letter. And the bounds are small enough that this is a totally valid solution. It works, it's great. And do you have any questions about that? Kind of a lot. No, well, we'll have time after this too. So if you come up with questions or you want me to run through something again, please tell me. Yeah, thank you so much.
All right, so that's the end of this week's session. So if you have any questions, comments, or concerns, please fill out the feedback form. A nice picture of Palca here. Yeah. And here's the link to the contest. So this contest was 5 problems. So each one, there are 2. I'm pretty sure there's 1 on shortest distance, 2 on connected components, and 2 on cycles. These are not ordered in difficulty. So please, if you read the problem, it's like seems pretty complicated, feel free to skip ahead, right? Look at all of them first. And yeah. All right. Thank you to everyone who came, and we'll end it here.